This is not an ordinary spring. Before military approval, it must pass standards far beyond ordinary parts. Each spring goes through 5 adjustments and 4 detailed inspections. When the finished piece finally comes out, the result is impressive. We are inside a large local steel mill. The process begins with steel bars. Every few days, large shipments of raw iron ore arrive from Australia. Because of its geology, Australian ore contains a high level of iron. Next, it moves by conveyor, where a gyratory crusher breaks it down. It looks like coarse sand, about 3 millimeters across. First, the iron ore is roasted at high heat. This makes sintered ore. Under that intense temperature, fine particles fuse, forming a solid mass. Once the material is ready, the next step is smelting. This machine is a blast furnace. Its numbered grid helps monitor the process. It is a probe system. A single blast furnace can require 400 to 1,000 tons of sintered ore. The black material is coke, though coal can also be used. Once the iron gate is sealed, high heat radiates from both sides, heating the ore evenly. This stage is fascinating. As the gate pushes inward, carbon reacts with the ore from below. But at this point, the sintered ore, not molten yet, instead, it forms dark, porous lumps. After a second roasting, the ore is moved forward to cool. Then it enters the blast furnace, where carbon monoxide reduces iron oxide into raw iron. The chemistry looks simple, but achieving it at this scale takes serious engineering. The cost, however, is enormous. The molten iron you see is the refined result. Before refinement, it still contains many impurities. High purity Australian ore produces relatively less slag. Lower grade ore is different. The slag has to be removed and reused. In some plants, hundreds of millions of tons are processed yearly, and a large share becomes slag. So where does that material go? Much of it goes into roads and asphalt. It is cheaper than natural stone. As steel leaves the furnace, gas is used to fine-tune the composition. Length and size are tightly standardized, with almost no room for error. Now the rolling process begins. This is where the steel bar takes shape. This long production line is a heavy-duty rolling mill. Once the hot bar enters the intake, the rollers pull it through and thin it down. It keeps shrinking until it is about finger thick. Then the machine ejects the steel rod. Now the ore is a rod. The next job is to turn it into a spring. First, 2 workers lift the heavy steel rod. Then it enters an electric furnace. Low-carbon steel often needs more than 1,200 degrees. It takes enormous heat. High-carbon steel is less demanding, so the quenching temperature usually stays below 1,200 degrees. 3 technicians wait at the furnace exit. The first grabs the hot steel tip, the second pushes it forward. The third controls the tool that starts the coiling. 1 steel rod is cut to the exact length of 1 spring. That means all 3 workers must move with real precision. They are handling a heavy, dangerous piece of steel. Mistakes ruin it. Look closely at this part of the footage. The front tool locks the spring head in place. Once it is braced, the steel rod keeps feeding forward. The alignment must stay perfect, with no visible deviation. At this stage, the ends are still unfinished, so the extra ends are cut away. Then it goes onto a cylindrical jig, ready for the next stage of processing. This part is critical. Only experienced workers can handle this station properly. Before cutting begins, the spring lies flat, so it can rotate and align correctly. Even a small change in speed can leave the cut uneven. After several minutes, The worker has finished cutting both faces, but the edges are still full of burrs. So the springs are moved to a surface grinder. The machine can hold 6 springs at a time, but it has only one high-speed grinding head. That means each of the 6 springs is ground one at a time. The benefit is consistent precision, with almost no tolerance. The drawback is speed. More grinding heads could raise output, but this line clearly favors control. Once the end grinding is finished, the worker with the angle grinder begins another pass. Any burrs or loose metal edges are carefully removed. The surface is worked smooth. No sharp metal should remain. Chamfered. Next, the springs move to heat treatment to increase hardness and improve strength. Each formed spring goes into an electric furnace for a 15-minute soak. This also helps correct the spacing between coils. So how is that spacing adjusted? Mostly by experience and observation. A steel plate is fixed to the table. A guide wire sits in the center. When the spring lies flat, the worker begins checking its position. If the gap is too narrow, the spring is tilted upward. Then, while it rotates, flatness is checked by eye. If the spring sits too high, it is pushed back down. The accuracy is impressive, but this work is not built for mass speed. Next, a frame holds the ends in place. This prevents deformation during quenching. Here, they use oil, compared with brine. Oil cools the steel more gently. The spring stays submerged for about 2 minutes. When smoke clears and temperature stabilizes, the workers lift the spring out with force. Each spring goes on a rack, then it is heated again. This time, the heating process is called tempering. To a controlled degree, tempering slightly lowers the hardness, but it improves toughness and flexibility. That balance is crucial. A spring is built to absorb shock and return to its original shape. You can see the oxidized scale on the surface. Now the springs move into finishing. The worker sets up the equipment, closes the iron door, and flips the switch. Soon, a new batch of springs is ready. This is careful work, not piece rate speed. In one full day, a line like this may not produce 100 pieces after the diameter is checked. The master places it in a small hydraulic press. Now they test its load-bearing strength. This is not random. Every spring must pass this inspection. If even one parameter fails, it is removed. Here you can see the setup is clear on the workbench. Surface marks are polished with a grinder. The contact area is made flat. Then deformation is observed under force. At the top, there is a ball-bearing style pressure point. Polishing helps it sit flush against the surface. As the hydraulic pressure rises, the ball bearing presses steadily on the spring. When the pressure reaches the required level, the spring can be removed. An instrument checks the contact surface. If cracks or exposed metal appear, the material has failed the standard. After compression, the groove should stay smooth and rounded. No cracks are allowed. Only then is it approved as military grade.